So, 5.3, connecting the graphs of f, f prime, and it should say f double prime. So we're going to add the second derivative to what we're doing in here. So we've dealt with increasing and decreasing and maximum, local max, local min, and absolute max, and absolute min, and how to find them. Take the derivative, set it equal to 0, or find out what's undefined to get the critical points. Today we're going to add the second derivative and all of its wonders into that as well. Now, the first derivative test, and we've actually did the first derivative test. If f prime changes from plus to minus, from positive to negative, on each side of a critical point, we have a local maximum. If f prime changes, bless you, from negative to positive on each side of a critical point, we have a local minimum. This was what our sign charts did. This is exactly what we were doing when we were dealing with our sign charts. And we had critical point and plus, minus, plus, when it goes from positive to negative. So if the derivative changes sign, then the original one goes from increasing to decreasing to increasing, and we have a max, and we have a min at those places where it changes sign. Remember, as some of you found out while working on your homework, just because you have a critical point does not mean that it's going to change sign, and you're not guaranteed a maximum or a minimum. And a critical point just means that something goofy is happening there instead. But if it does change sign, if the derivative changes sign, you have a local max or min. This is called the first derivative test, because you use the first derivative to determine whether or not you have a local max or min. The sign chart is application of the first derivative test. It works very, very well. Okay. Concavity. The function is concave up on an interval I if its derivative is increasing on that same said interval. So if the derivative is increasing, then the function is concave up. If the derivative is decreasing, then it is concave down. In other words, if the derivative, if f prime is getting larger, then it is concave up. If the derivative is getting smaller, if f prime is getting smaller, it is concave down. Okay. How can we register? How can we figure out where the derivative, where f prime is increasing and where f prime is decreasing? How do we find out where a function is increasing or decreasing? We just talked about that. You take its derivative. If the derivative of a function is positive, it's increasing. If the derivative of a function is negative, it's decreasing. How can we find out where f prime is increasing or decreasing? Where its derivative is positive or negative. Thus, we come up with a concavity test. A twice differentiable function. A twice differentiable function, i.e. the derivative has to exist and its derivative has to exist. So you have to be able to take, you have to have a function where you take its derivative and the second derivative both have to happen. It is concave up where the second derivative is greater than 0, i.e. positive. Concave down where the second derivative is less than 0, i.e. negative. If the second derivative is positive, it's concave up. If the second derivative is negative, it's concave down. Concave up, concave down. Okay, that's the first, getting applause. But I will honestly say this. I've had students that laugh and giggle when I do this concave up and concave down. I have a former student who actually became a math teacher. At one point, when she was doing her student teaching, she taught this lesson to her students. And they laughed when she did the concave up and concave down. And she says, you laugh. But that's what my teacher taught me, and I remember it 10 years later. Because it works, and this is one of those things. If the second derivative is positive, it's concave up. If the second derivative is negative, it's concave down. That's concavity. So here's what's really cool. We can, from an equation, get a really good idea what's going on with the function now. We can find max and min. We can find where it's going up and where it's going down, where it's concave up and where it's concave down. Remember, concavity is not necessarily increasing or decreasing. It means it curves up or curves down. And we can get a really good idea what's going on now with them. Really good idea what's going on with them now. Anybody need more time getting this down? Okay. So let's do an application. Let f of x equals 3 plus sine x on the interval from 0 to 2 pi, because of trig functions, you really want to limit the interval. Otherwise, you're going to have repeated max and mins and concavities and all kinds of crap going on. So you really, really, really want to limit the interval whenever you're dealing with trig functions. Over which interval is this function concave up and concave down? So what we want to do is do essentially the second derivative. We want to find the second derivative, find out where it's positive or negative. So to find the second derivative, we need to find the first derivative. F prime, derivative of 3 is 0. The derivative of the sine is the cosine of x. F double prime x is the negative sine of x. Easy enough. And where is the second derivative equal to 0? Because what are we looking for? We're looking for where it's concave up and where it's concave down. Concave up, it's positive. Concave down, second derivative is negative. What happens between positive and negative? 0. So what do we want to find? We want to find where it's equal to 0. So f double prime is equal to 0. Where? Where's the sine equal to 0? The sine of x is equal to 0 at x equals 0. And pi, and 2 pi. And those are the only ones that are in our interval. And that's what we care about, is we care about our interval. So here's what we do. We make up a sign chart. And we have 0, and we have pi, and we have 2 pi. And we don't really have to worry about anything after that, before or after the 0 to 2 pi, because those are the ends of our intervals. So we have one place where the second derivative is negative, is 0. Now we need to find, okay, is it positive in the interval or negative in the interval? Just like the derivative, the second derivative, same thing. These points are the only places where it's going to be 0. Everywhere else is going to be concave up or concave down accordingly. So I pick a number between 0 and pi. Let's say pi over 2. Put pi over 2 into negative sine. Pi over 2, the sine of pi over 2 is 1. Negative of that would be negative 1, so it's negative. Pick a number between pi and 2 pi. Oh, I know. 3 pi over 2. The sine of 3 pi over 2 is negative 1. However, we're dealing with the negative sign, so it would be positive 1. So f double prime is positive and negative, which means f, the original function, is concave down and concave up.
Is that how we write it usually?
Yes. So all you're doing is this. You're doing, when you're looking for concavity, you're looking for, you do a sign chart for the second derivative. It tells you all about concavity. You don't want to use the same sign chart that you used for the first derivative. two separate sign charts, one for each. Okay. Now, the point at which the graph has a tangent line and changes concavity is called the point of inflection. Your point of inflection, your PI, is where concavity changes. But it has to have a tangent line. It can't be a place where the second derivative, well, kind of it can be the second place where the second derivative doesn't exist. All you're looking for is your point of inflection, your PI, is where it changes concavity. For this one here, point of inflection is x equals pi. That's where I change concavity. I go from concave down to concave up at that point of inflection. I go from curving down to curving up at that point. Just like the first derivative, a 0 on the second derivative does not guarantee a point of inflection. Now, it is a very funky looking graph that has a 0 for the second derivative and does not change concavity. It is a very funky one. Probably the ones I could think of would be a cusp, would probably be one of the most common ones. Just think about it, concave down comes together at a cusp. Would not change concavity, but once again, we'd still have a 0 or undefined for the second derivative. Okay, it doesn't happen very often. Usually if the second derivative is 0, you have a point of inflection. If it's undefined, that's where you might not have a point of inflection and might not change concavity. Kind of depends. Once again, there are no guarantees, but those would be the only places where it can happen. Just like the critical points, the only places where you might have a maximum or minimum. There's no guarantee there's one there, but it's the only place where it can happen. Where the second derivative is 0 or undefined, and the only places where you might change concavity, but it's not guaranteed to change concavity. Won't happen anywhere else, but it might happen there. Okay. The second derivative test, and we don't use the second derivative test very often. Okay, so the second derivative test, if f double prime of c is positive, then c is a local max, but there is something missing from the second derivative test. C is a critical point. So rather than the second derivative test, is another way of finding max and min other than the sign chart. Frankly, sign charts are more useful from the standpoint of they're generally easier to do. You don't have to take the second derivative with a sign chart to find max and min. And you're often asked to find out where things are increasing or decreasing. And if you know where they're increasing or decreasing, you don't have to do the max or min. The second derivative test is just another way of determining whether you have a maximum or a minimum. You find a critical point, take that critical point, put it into the second derivative. If the second derivative is greater than 0, you have a local minimum, because what's going on if the second derivative is positive, it's concave up, which means it's looping up, and your critical point is part of the concave down thing. Therefore, it's a local minimum. If you take the critical point, put it in the second derivative, and you get you get negative, then you have your local maximum. Because what's going on here, this one, you have a critical point, which means you have a horizontal tangent line. But if it's greater than 0, it means it's concave up. So what do I have? I have a minimum. Yes.
So is that critical point from that first derivative?
From the first derivative. Critical points from the first derivative. You do not get critical points from the second derivative. You get possible points of inflection. Okay? So you plug it into the first derivative. If it's you take the critical point from the first derivative, plug it into the second derivative. If it's greater than 0, it's a local minimum. If it's less than 0, it's a local maximum. Rarely do we use this for actually determining max and minimum. However, I could see this coming up on an AP question. You know, if this is true and this is true, if f prime equals 0 and f double prime is this, do you have a local max? Do you have a local min? That kind of a question. Which of the following are true? First derivative 0, second, you know, which of the following are possibilities? That kind of stuff. This is what can help you. So I'm going to tell you, if I ever see anything that tells me the first derivative is, the second derivative is positive, I'm putting a little happy sign next to it so I know what I'm talking about. I know I'm dealing with something that's concave up. Because the only reason to tell me that the second derivative is positive is to tell me it's concave up. The only reason to tell me the second derivative is negative is to tell me it's concave down. That's really the only reason to do either one of those things for the most part. 90% of the time, that's all you really care about from the second derivative being positive or negative is whether it curves up or down. That's it. And so if I have an AP question that gives me list information about a function, oh, it's twice differentiable, and from here to here, the second derivative is negative. Oh, that means from here to here, it's concave down. So I have an idea what it looks like. That's all that's about. Okay, and we'll get to AP questions, practice ones later on in the year. You'll kind of see all this will all be tied together at that point. I'm just kind of foreshadowing as much as I can. Okay? So, putting it all together. Find the relative extrema, i.e. max and mins. The intervals over which the function is increasing or decreasing. The points of inflection and the intervals over which the function is concave up or concave down. I have given you the tools over the last 3 lectures, including today's, to answer all of that for one problem. It gives you a really good idea what's going on here. So here's what I want you to do. Answer that question with that problem. So here we go. So the first thing you want to do is take the derivative. 3x squared minus 2x minus 5. And when in doubt, take the derivative, set it equal to 0. It's really going to become a big deal in the next section we do. So f prime equals 0 at x equals -1. Guys, and at 5/3. Okay, factor it, set it equal to 0. Those are your zeros. Set up a sign chart. -1, 5/3, f prime, positive or negative. I try a number smaller than -1, -100. I take -100 and square it, and that's much bigger than all the rest of the crap combined. So that's positive. I pick a number between -1 and 5/3 and plug it in 0. Put in 0 in the second derivative, I get a negative. Plug a number larger than 5/3 in there, 100. Take 100 and square it times 3. That's much bigger than the rest of it. It's positive, which means that f is increasing, decreasing, increasing, max, min. Okay. Part 2, and I have not answered my questions yet. I'm strictly doing the groundwork to answer my questions. Second part, take the second derivative for my concavity. F double prime of x equals 6x minus 2. F double prime equals 0 at x equals, what is this, 1/3? Yeah, second derivative, yeah, 1/3. Okay. F double prime, set up a sign chart that's equal to 0 at 1/3. A number smaller than 1/3, 0. That's negative. A number larger than 1/3, a gazillion, 10. that's positive. It's concave down, concave up. And if you know anything about the original problem, this also makes sense, does it not? It's a cubic. What do cubics look like? Part of the reason why we pick problems like this is because they're easy to work with, and you should have an idea what it looks like anyways. All we've done is locate the places. Now, so to answer my question, it is increasing from negative infinity to negative 1, and from 5/3 to infinity. It is decreasing from negative 1 to 5/3. I have a max at x equals negative 1. I have a min at x equals positive 5/3. It is concave up from 1/3 to infinity, concave down from negative infinity to 1/3, and it has a point of inflection at x equals 1/3. Now, notice I said where the maximums and minimum and the point of inflection are. I did not say what they are. There's a difference. All I have found is where everything is happening. I have not found any corresponding values. All my corresponding values come from the original function. I have just located where. I don't know what the actual relative maximum is. I just know where it happens. That's all I have figured out is where does it actually happen. Not what it actually is, but where it actually happens at. Okay, not what it actually is. To find out what it actually is, what do I need to do? I need to plug it into the original problem. Now, if I take negative 1 and plug it in there, I end up getting, let's see, that's negative 1. That's also negative 1, positive 5, negative 5, so that part's 0. So I get what? Negative 2. So I have a local maximum at point x equals negative 1. It's actually negative 1, negative 2 is the absolute, is the local maximum. The minimum, 5/3, and negative 2029.8. The exact value is actually negative 54,805.27. You should learn how to do fractions on your calculators so you can evaluate a polynomial at a fraction with relative ease. You really should. Just makes life easier. Okay. And then my point of inflection, I can locate that. Same thing, plug in 1/3 into the original one. So 1/3 cubed minus 1/3 squared minus 5 times 1/3 minus 5 equals negative 182/27. So my point of inflection takes place at 1/3, negative 182/27. And I can sketch those points on the graph if I wish to do so or need to do so. I have my high point, my low point, and I have it where it changes curve angles. And then I can kind of sketch everything in between because I know what's going on. It's going up, it's going down, it's curving this way, it's curving that way. I've got a really good picture of what that graph looks like. It goes up, and it goes up to here, comes down, and then goes back up, and it's got a nice little curve until it's somewhere in between here, and then it starts curving the other way. I can figure out where my zeros are. I can figure out where it crosses the y-axis. I can get a few really good points, and then I can sketch in what's going in between. I don't know the exact points, but I can get a really good idea what it's supposed to look like. Any questions on this problem? Yes.
Do you want to start it on like the coordinate form, or can we just write like for the maximum?
Depends. Depends. So the question was. Shh. The question was, do I just say this part, or do I need to say this part? If you give me a coordinate, you've covered both bases. That's a safe one to do. But what is the question asking me? My original question says, find the relative extrema. Okay, saying it happens at x equals -1 and x equals 5/3 does not actually tell me my relative max and minimum. The y coordinates are the ones that answer that point. If it says, where do they occur, just give me the x's. But if it says, what is it, you need to give me the y's. Where is x, what is y? That's a huge thing to remember. Where is x, what is y? You got to know those.
On an AP test, if they're to ask,
They're usually pretty clear about it.
they like to say where, and you just if you put a
If you say where and if they say where and you put a coordinate, they'll take that because you found out where it happens. You're giving the x coordinate. They'll do that. And I've seen them do both. I've seen them ask where and I've seen them ask what. If they ask what and you just give the x only, you will not get the point. Now, if it's a multiple choice, obviously it's there. But if it's not a multiple choice and you have to show your work, that's where it gets a little pickier how you answer the question. Okay, multiple choice is multiple choice. The answer is there. I honestly do not recall ever seeing none of the above as any choice on any of the AP multiple choice questions I have ever seen for any of these, any of the stuff. There's always an answer for every one of them. There's always an answer. There will be something there. You won't have none of the above, which means if you screw up, you answer that one rather than what it should be. The answer's there. Okay? But they also remember they do give the most obvious incorrect answers. Yes?
So for the point of inflection, real quick.
Yeah.
The second derivative, what x equals, where do you plug that back into?
I plug it in to find where it's concave up. You put it into the second derivative. The second derivative tells you what's happening. So the second derivative is positive and negative, which means the first derivative is concave up and concave down. Same as doing a sign chart for increasing and decreasing. Where the first derivative is positive, the original function is increasing. Where the first derivative is negative, it's decreasing. Where the first derivative is negative, it's concave down. A second derivative is negative, it's concave down. The second derivative is positive, it's concave up. Sign charts work exactly the same. You find your possible points of inflection from the second derivative. You plug values into the second derivative to see where it's positive and negative to tell you what's happening with the first derivative, with the original function. Okay. So that's what's going on. Questions? Okay, so we do not have enough time to finish this together in class. So what we'll do is we will come back Wednesday, and we will do this one together. I will actually go over to the beginning class. I want you guys to do this one on your own. Yeah, that's part of the homework kind of thing. In your notes, do it in your notes, just add it onto your notes. Okay, and we will do this together. Same questions before. Find the relative extrema, intervals where it's increasing, decreasing, points of inflection, intervals over it's in concave up, concave down. 1 over x times e to the 1 over x. When you have exponentials are never equal to 0, but they might be undefined. Hint, 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 hint. Factoring will help you find your zeros.